All right, so now to finish the last couple questions of this class notes, we're going to perform each two complement addition using A-bit arithmetics. So remember that we're going to discard any carry out of the most significant bit after adding, and we're going to decode the result and verify that it matches the expected decimal answer. So first we have 45 minus 30. So once again, the most easiest way to approach this is we're gonna set up this in 8 bits, and then we're gonna add the numbers. So if I represent 45, 45 will be 0, 0, 1, 0, 1, 1, 0, 1. So this will be 45, and then minus 30. Well, or really, if I take 30, this is going to be 0, 0, 0, 1, 1, 1, 1, 0. But we need minus 30, so minus 30 really is, I'm going to flip it, and then I'm going to add 1. So if I flip it, I get 1, 1, 1, 0, 0, 0, 0, 1. But then because I'm going to flip it, I'm going to do the plus 1 part. Then I'm going to get 1, 1, 1, 0, and then 0, 0, 1, 0. So this is my final result for what minus 30 representation is. So this is first the flip, and then the addition of 1. 1 plus 1, 0, carry 1 is going to give me the 0 here. Okay, so at this point, now if I'm going to do 45 plus minus 30, what I'm really doing is 45 here minus 30, and I'm doing this representation here, which will be 0, 0, 1, 0, 1, 1, 0, 1, added with this, which is 1, 1, 1, 0, 0, 0, 1, 0. And if I add this, this is going to give me 1 plus 0 is going to be 1, 0 plus 1, 1, 1 plus 0, 1, 1 plus 0, 1, 0 plus 0, 0, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1. But remember, because we're doing two complement, then in here, we're not going to carry out the most significant bit after. So this one that normally will show up in here is not going to show up in here, and this is going to be our representation on this type of arithmetic. So now, if you look for what this is going to be 15 and base 10, which kind of makes sense, 45 minus 30. Okay, so now if I'm going to do the same thing, notice that I can, now I'm going to do minus 45 plus minus 30. So if I'm going to do minus 45, I already have first the flip from 45. So it will be 1, 1, 0, 1, 0, 0, 1, 0. But then I'm going to add plus 1. So it's going to give me 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1. Okay. And I also have what is the minus 30 from this one. So I already know that this is 1, 1, 1, 0, 0, 0, 1, 0. So if I add those two numbers, if I add those two numbers here, I'm going to have that this is 1, 0, 1, 0, and then 1, 1, 1, 0, 1. And I will have 1, but then we're not going to carry the most significant bit. Okay. So now what this number is going to be equivalent to 75, which kind of makes sense, or really, because I had to flip, the result is being negative, since the most significant bit that I'm not carrying is 1. That's going to tell me that my result at the end is minus 75. So I don't carry the most significant bit. I discard it, but I should be aware of it for the fact that I have a sign. So if the most significant bit is a 0, then it doesn't change it. It's going to be positive. But if it's 1, then it's going to give me a negative value. So we have that this is minus 75, which kind of makes sense with minus 40, minus 45, minus 30. Okay. Now, question 11, we're going to do something similar. So for each of the additions below, we want to determine whether an overflow is going to occur, and justify your answer using the same sign, opposite sign rule without converting to decimal first. Okay, so if I add these numbers, and of course this is much more easier to see if I'm just writing it as 0, 1, 1, 0, 0, 0, 0, 0, and then adding to 0, 1, 0, 1, 0, 0, 0, 0. Okay, so if I add this, I get 4 zeros here, then I get 1 here, 1 here. 1 plus 1 is 0. I carry 1, I get this. Okay, so now in here, notice that I had this number. The most significant bit here is going to be 1. So this is going to be a negative number. So overflow has occurred. So overflow occur. Okay. So in terms of checking, notice that this is 96. This is equivalent to 96. And this other number is occurring, is equivalent to 80. So the sum should be 176. But that's much more bigger than 127. Which will be the maximum number of bits that we can get with this, because the A sign bit tops is gonna get to 127. Okay. All right. So now for B, we do a similar thing. So let's set up the sum. So we have 1 0 0 1 0 0 0 0, and then 1 1 0 0 0 0 0 0. So if I add this, I'm gonna have 0 0 0 0, and then 1 0 1, and then I'm gonna have 0 here. And of course, I'm not writing the most significant bit. The most significant bit here, I discard the one that it comes after this, but the most significant bit from here is 0, so this is going to be a positive number. Okay, so here overflow has occurred because we have a negative plus a negative giving positive. So and this is going to be impossible in correct arithmetics. This happens because this is equivalent to the number minus 112, and this is equivalent to the number minus 64. So when you get to this is really the number minus 176, which is going to be less than minus 128. So this confirms that you're doing an overflow. Remember that we have that for base 8 here, for 8-bit arithmetics, then we go from minus 128 to 127. So we're going beyond that. We're actually going beyond what we need. And we are occurring in an overflow. Now, question number 12 says, the slide state that a carry out of the most significant bit is normal and it must be dropped, or it is not overflow. So let's give a concrete example with a bit example with a specific bit patterns that show that a carry out of the most significant bit can occur without overflow, and display why dropping the carry gives the correct results. So the example here is going to be very simple. It's going to be -1 plus +1. And so, of course, that's going to be 0 in normal circumstances. If I write this, -1 is just going to be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, just did an extra 1. And if I add 1, then of course this is 0, 0, 0, 0, 0, 0, 0, 1. Remember that this is -1 because we flip all the terms and we add 1. So that's why we get all this becoming zeros, and then we add 1 at the end. And so that's why it becomes this. So this 0 transforms into 1 back again. Now if I add this, if I add these two quantities, then notice that you're going to get 0, 0, 0, 0, 0, 0, 0. Okay? And you have a 1 that is doing the carry out. This is 1 with 1, 0, carry 1, 1 with 1, 0, carry 1, 1 with 1, 0, carry 1, until the very end. You're going to have 1 with 1, 0, carry 1, 1 with 1, 0. And so the most significant bit that we're going to have, or the discarding, is going to be 1, so which is the carry out. Carry out is 1. This is correct because we don't have any overflow. We actually got 0, so no overflow occur. And this happens because the operands has opposite signs. So we have 1 positive and 1 negative. So overflow is impossible by the same sign rule. The carry out here of the most significant bit is going to end up being an artifact of modular wraparound arithmetics, and from the fact that 2 to the 8 is 256. So the true sum here of -1 plus 1 is equal to 0 is going to differ from the 9-bit results of this, which will be 256 plus 0, by exactly 1 multiple of 256. All right, so with this, we're kind of getting to the end of n-based arithmetics. We have a couple of extra big problems that are an extension of this. So problem 13, 14, and 15 are special problems that they represent an extension of if we're going further than in this representation. So you can be doing 4-bit to complement or multiple other representations. So I'm going to leave those for the solutions that I make on at the end of the week, so you can check on those because they're pretty large. So discussing them probably will take me another entire video, and we're already going on the third video on this, so we're just gonna cap it here. So for now, this is the main basic of all the arithmetics that we can do with this. Hopefully that makes sense, but continue practicing for the rest of the section.